Good morning, class. We are looking at section 4.9, antiderivatives. Okay. So we discussed optimization problems and Newton's method. In short, Newton's method is really what's called the equation of a tangent line, using that and setting y equal to 0. Okay, so y minus f of x of 1, this is y minus y1 equals m times x minus x of 1, and setting y equal to 0. So you use the tangent line, you set y equal to 0, and that gives you an approximation for the next point. And you move on until you achieve what you're looking for, known as Newton's method. Also, the calculator methodology is given to you because it can get very tedious. All right, the anti-differentiation basically is the reverse process. It's important to know when we differentiate class, we get a unique answer. By the way, the notation is normally we use the following notation: capital F prime equals lowercase f. So the uppercase is the antiderivative. So when we differentiate, we get one function, but if we go with the reverse process, it's not unique, and that's important for everybody to know. The antiderivative is not unique. Why is that? Because the derivative of any constant is 0, therefore it results in a family of functions. So having said that, as an example, when we are dealing with x squared, the antiderivative is 1/3 x cubed, and we have a c which represents a constant. It's a constant of integration. So having said that, the notation that is used here, it's an elongated s, short for summation, and x squared dx. Okay, the anatomy of that will be explained with details later on. But this is the notation that is asking for integration or anti-differentiation, and it becomes 1/3 x cubed plus a constant. It's important that dx tells you what is your independent variable. Now, the last thing, if f and g are any two antiderivatives, then they differ by a constant. In other words, if you have capital F of x and differentiate it, you get capital F prime. If you have capital G of x, you get capital G prime. And both of them are equal to lowercase f of x, the difference is just a constant. Okay. All right. Let's get started with some warm-up examples. Okay. And then we get to the heart of the matter. The integral of 8 dx, again, I can't emphasize this enough. Dx, again, let me write this one and remind you that, remember, dy dx equals f prime of x. We had this, everybody remembers that. And then we would use dy as f prime dx, okay? So that's the same dx, okay? And that shows you what is the independent variable. And so we are thinking of a function whose derivative is 8. Obviously, the answer is 8x and a constant. And the reason is very simple. In the beginning, you differentiate and you check. So differentiate the right side. You get 8 and it works. So I hope everybody can see how things work out. So for now, we are asking ourselves, what is the function we are looking for? When we differentiate, we get it. Now, how about this one here? Can anybody tell me what function we need to differentiate to get 3x squared? Anyone?
X cubed.
Beautiful. X cubed plus a constant, and you can check by differentiating the right side. Okay. What function should we differentiate to get e to the power of x?
E to the power of x?
It's itself e to the power of x and therefore a constant. Okay. Now we differentiate the right side to show we haven't made a mistake. Finally, for a warm-up example, what function do you differentiate to get to 1 over x? Natural log. And so we check that by writing it in this fashion. By the way, we use ln and we put in an absolute value because of the limitation on the domain. As you recall, the domain is 0 to infinity. So now we are looking at some rules, okay, that I hope everybody is comfortable with. So let's go over them quickly. If we have a number, which and dx, the answer is kx plus a constant. I want to go over the power rule quickly. First differentiation class. If I want to differentiate x to the power of n, differentiation gives me n x to the power of n minus 1. Now, I want to reverse the process. Remember, that's the idea behind anti-differentiation. So what did we do in the differentiation? We subtracted 1 from the exponent and we multiplied by n. Now, what would be the reverse process? Instead of subtraction, we're going to add 1. Instead of multiplication, we're going to divide. So therefore, when we integrate x to the power of n dx, we get x to the power of n plus 1 over n plus 1 and a constant. This is the power rule. It works for every power except n equals -1. In this case, we go to number 5. And there are different ways of writing it. We're going to write all of them. X to the power minus 1 dx, 1 over x dx, dx over x. They all mean the same thing. The answer is natural log and a constant. This is obvious. If you are multiplying by a function, the differentiation and the integration makes no difference. That remains as a multiplier, as a coefficient. If you're differentiating or integrating a bunch of terms, you do them term by term. Okay. All right, let's go here. We multiply by k if we are differentiating. We divide by k if we are integrating e to the power of kx. The derivative of sine is cosine, so the integral of cosine is sine. The derivative of cosine is sine, negative sine, and the integral of sine becomes minus cosine. More, the derivative of tangent is secant squared, so the integral of secant squared is tan x, and the rest of them follow class. And there's more coming up we will look at. So those are some differentiation formulas. We will look at each and every one of them more carefully in a moment. Let's start with power rule. So x to the power of 7 dx. What are we looking for? We are looking at the power rule. So we're going to add 1 to the exponent, becomes 8, and we're going to divide by it. 1 over 8, x to the power of 8 plus a constant. And I hope you can do that in one shot. You don't have to write the intermediate step. We are getting it started. I thought maybe we write that. So can anybody tell me what's the answer here? (99) we add 1 becomes 100. So x to the power of 100 over 100 and a constant. Again, whether you write that x to the power of 100 over 100 or you write 1 over 100 times x to the power of 100 makes no difference. That's your choice. They all mean the same thing. Now, when we did the differentiation here, what did we do? Because we are going to do the same thing, meaning we are going to use algebraic step first. What did we do first, class? To be able to differentiate this, do you remember? We wrote this as x to the power of 1/2. So we do exactly the same thing. Therefore, we can use the power rule. All right, so 1 divided by 1/2 plus 1, x to the power of 1/2 plus 1. and a constant. So what is 1/2 plus 1? 3/2. What is 1/3 is 2/3. You can leave it like that, or you can write it as such. Either way is fine. All right. Same thing here. What did we do when we were differentiating? We changed it to x to the power of -3. Therefore, we could use the power rule. So 1/-3 plus 1, x to the power of -3 plus 1. Obviously, -3 plus 1 is -2, right, everybody? And so you put it underneath, and that takes care of the business. Okay. You make sure get rid of the negative exponent class and make it positive by putting it in the denominator. All right, let's see what happens here. We are dealing with exponentials. The answer is always in itself, whether we differentiate or integrate. However, in the case of integration, we divide by 4. Okay, divide by 4. In this case, we divide by -3. What about this case? Okay, first, let me change this to 1/2 x, just because I want to make sure we don't, mix up. We realize the exponent is 1/2 x, which means the coefficient of x is 1/2. So we divide 1 by 1/2, and that gives us 2. Okay, class? Okay, 1 by 1/2, and it gives us 2. 2/x, if we see that as a natural log, by all means. If we don't, maybe you want to write this as 2 times 1/x. Now we can see it's 2 times ln x and a constant. Okay, class? Now that it's easy to see. Same thing here. If you see it, fine. If not, do rewrite this as 1/2 times 1/x. So that's 1/2 the natural log and a constant. Again, the reason we are writing it in this fashion or in this fashion, so it makes it easy to see that 1/x is there, and that's what you're really integrating. Now 1/2 or 2, either one, is just a multiplier, a coefficient, and remains intact. Okay, so I hope everybody can see that. All right, so what happens here, we are going to do this term by term. Term by term. Okay, everybody, let's do that. 2x to the power of 4 becomes 2/5 x to the power of 5. 3/4 x to the power of 4 minus 7/3 x cubed plus 1/2 x squared, because remember, this is x to the power of 1. So 1 and 1 becomes 2, 1/2 x squared minus 5x plus a constant. Step by step, everybody, step by step. X minus 5 squared, again, we do the math, we do the algebra, and we square this. x squared, 1/3 x cubed, minus 10 divided by 2, that means minus 5x squared, plus 25x and a constant. We are looking at power rules, okay, class? What do we do here? Same thing as differentiation. We simplify first. How? We make up 3 fractions. This is one of them, x squared over x squared, which is 1. This is another one, minus 7x over x squared, or minus 7 over x. And the last one is 2 over x squared. Okay, everybody? First, we make up 3 fractions. Now, 1 obviously gives you x. By the way, pay attention that this is the x. 1 gives you x minus 7 over x minus 7 ln x. I want to show you the last one. Two x to the power of negative 2. So you are going to divide 2 by negative 2 plus 1. The exponent is negative 2 plus 1. Remember, negative 2 plus 1 is negative 1. So you have negative 2x to the power of negative 1. Negative 2x to the power of negative 1 is negative 2 over x and a constant. In fact, let's just, this is easier to see, 2x to the power of negative 2, okay? All right. We are integrating this. It's extremely important to see you're dealing with dt. Therefore, 1 doesn't give you x, it gives you t. Cosine, the derivative of what is cosine? Sine. So t plus sine t and a constant. Okay. We've seen this root function first, so we write it as x to the power of 1/3. And that one, class, is 1 over 1/3 plus 1 x to the power of 1/3 plus 1. Now, 1/3 plus 1 is 4/3. Okay. So 1 over 4/3 becomes 3/4. And then minus sign gives you plus cosine x and then a constant. Now, 3/4 x to the power of 4/3. 3/4 x to the power of 4/3. And using the roots is the cube root of x. This is 3/4 x to the power of 4/3. And x to the power of 4/3 is cube root of x to the power of 4. Or one may even write this part, you can even write it as x cube root of x. Okay, just in case. But that's fine. The next thing we're going to look at is solving differential equations, specifically initial value problems. So first and foremost, here's the definition. Any equation that contains a derivative is called a differential equation. A function which satisfies the equation is called a solution to that. An initial value problem is a differential equation along with a specified value of an unknown function called the initial condition. Meaning, what we have been doing so far, everything has been really, when you do integration, you're doing differential equation. But the difference is now, a pair is given, meaning 0, 1. So far we have been coming up with a family of functions. Remember the effect of C. The C takes the function up and down along the y-axis. So now you have a family of functions with the c. This will get rid of the c, but for now, let's just treat it like before to get it started. To get us started, first and foremost, dp dt means p prime of t, so dp is 2e to the power of 3t dt. When you integrate both sides, the left side gives you p of t, and the right side we do the integration, which is a simple integration, and is 2/3 e to the power of 3t plus a constant. Now, this is done if we didn't have the pair. This is just like previous examples. This is a family of function. This is called a general solution. Okay, everyone, you have a general solution. So what we have been doing so far, solving for a general solution. Okay, fine. And we would be done, except we have a pair with coordinates 0, 1. That means replace the t with 0, everybody, and p of t with 1. Let's do that. Of course, 3 times 0 is 0, e to the power of 0 is 1. So 2/3 plus some number is 1, and that becomes simply 1/3. Now you replace that, and this is a specific solution, okay, particular solution. Cool. Why is it? Because now we know what's the constant. So over here is a general solution. Over here is one specific solution or a particular solution. Okay, class? All right, continuing with these thoughts, first of all, this refers to the pair 1, 5. And by the way, it's not necessarily initial value problem, because initial value problem normally refers to x being 0. So it's just a boundary problem, if you will. But for now, let's do the integration as follows. dy is the right side times dx. Integration will give us y, or f of x, equals to the integral of the right side. And that is something we should be comfortable with. We've done this before. 1 over x, we know that. Square root of x, change it to x to the power of 1/2. Bring it up, becomes negative 1/2. And that is a simple integration using the power rule, everybody. So again, 1 over x, we know it gives us natural log. This one is 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1, and a constant. 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1. And they add up to 1/2, as you know. 1/2. And this one is 1 over 1/2, or 2, and the other one is square root of x. And this is a general solution. And we would be done if we were looking for a general solution. However, we are given a pair 1, 5, which means we are going to replace the x with 1, everybody. And we get 5. I hope you know that ln 1 is 0, and this is simply 2, and c becomes number 3. And now this is a particular solution. Okay, very straightforward. Let's look at this example. We are interested in integrating x plus 1 over square root of x. And if we were differentiating, we would do absolutely the same, which means we are going to simplify this by making up 2 fractions, everybody. All right, square root of x is x to the power of 1/2, and we get this. By the way, I'm hoping you can go from here to here in no time. Do you have to take all those steps? I hope not. And both cases, we've done both of them previously, so you really should know it's 1 over 1/2 plus 1 x to the power of 1/2 plus 1. The other one is 1 over negative 1/2 plus 1 x to the power of negative 1/2 plus 1 and a constant. Okay, so 1/2 plus 1, everybody, 1/2 plus 1 is 3/2. Negative 1/2 plus 1 is 1/2. Okay, so this division by 3/2 meaning 2/3. Division by 1/2 means 2. Okay, so I hope everybody is comfortable with that. There's really not much to it. All right, we want to do this one, and we are going to do exactly the same thing. We cut it into 2 fractions. The first one gives you x. The next one is 2 x to the power of negative 2. We have done this class. I suggest you go find it in your notes. We have done this. Just change this to 2 x to the power of negative 2, divide by negative 2 plus 1, okay, and then x to the power of negative 2 plus 1. It's been done. Secant squared, I hope you know it's tan x and a constant. So this one goes from here to here. We have done that a couple of times. Make sure you can find it in your notes. Okay, everybody, make sure you can find it in your notes. Okay. Let's look at this case known as rectilinear motion. A particle moves in a straight line and has an acceleration. That's why it's called rectilinear, moving in a straight line. With the acceleration that is 60 plus 4, the initial velocity is negative 6 centimeters per second. Initial displacement S of 0 is 9. We want to find the position function. And I hope you remember that when we had the distance or position function, we would differentiate it. We get velocity function. Differentiated again, we would get acceleration. We are reversing the process. We are integrating everybody. So we're going to integrate A of t to get V of t. So integration, when you integrate that, 60 plus 4, it results in what? 6 over 2t squared plus 4t and a constant. All right. We know V of 0 is negative 6. So this is negative 6. Replace the t with 0. I hope you realize if you replace this one with negative 6, and this is 0, and this is 0, c becomes negative 6. And now you have V of t. Again, it's the initial value problem. The next one is finding the position function, okay? So the position function, we are going to integrate this one now. So 3 over 3t cubed plus 4 over 2t squared minus 6t and another constant. Now, if you use the same c, it's awkward because it's really not the same constant, but I know what you mean. I suggest you use it different. So instead of c, you can use C1 and C2, or you can see C and D. Understand why I'm using D, meaning this is not the same as that one. Okay, and we know S of 0 is 9. So plug in. So this is 9, 0, 0, 0, and you find D. Okay, and this is it. Now, let's make it general, something you've seen in physics, I guess. So let's generalize this for a case which is due to gravitational force, the G force. Show that for motion in a straight line with constant acceleration, okay, with the initial velocity of v sub 0 and the initial displacement of s sub 0, the displacement after time t is the following. S of t is 1/2 at squared plus v0 t plus s sub 0. I hope you remember this from physics. And due to gravitational force, let's see, due to gravitational force, we would say h of t is 1/2 gt squared plus v0t plus h sub 0. I hope you remember that formula also. Okay, where the g force, or 9.8 meter per square second, is at work. All right, so we are saying that it's a constant acceleration class. So it's just some number, 5, 10, 2. We just don't know what it is. So let's call it A. How about that? The acceleration is constant. Let's call it A. All right. So if this is the acceleration, the V is what? The integral of A. Okay. And the integral of A is AT plus a constant. All right. Now, the initial velocity is V sub 0. That means V of 0 is V sub 0. That's the meaning of it. S of 0 is S sub 0. So we replace it. V of 0 is a constant. Okay. If you plug in, if you replace the t with 0, this becomes c. On the other hand, we know it's V sub 0. So the constant is that. Okay. And so your V of t becomes AT plus V sub 0. Let's integrate. Okay. Again. So t to the power of 1, you have to add 1, becomes 2. So divided by 2, 1/2 AT squared plus V0t plus another constant. Another constant. Again, notice I had C here. I don't want to use the same thing. I'm going to use D on purpose, something different. You can use C sub 1 and C sub 2. What is S of 0? Plug in T equals 0, and you get D on the one hand. On the other hand is S sub 0. They must be the same. And so your formula now, replace the D with S sub 0, and that is the proof of the formula. You can do exactly the same thing due to gravitational force.